Hi, this is Abee Alazzwi. I'm going to talk about Mu bringing Internet of Things to noise cancellations.
And this is Stephen Nery. In this presentation, we're going to cover a brief summary of the paper, give an overview of noise cancellation, the look-ahead algorithm that the researchers used in this paper. We're going to cover the mute system architecture, that's the hardware, and a brief covering of some of the algorithms, their experimental evaluation, which includes the results, the current limitations as stated by the researchers of their device, and end with a quick discussion and conclusion. In this paper, researchers propose an active noise-canceling solution by exploiting the time delay between RF signals and sound waves. Their custom solution consists of several wireless relays in a room which listen to the ambient noise in the room and use DSP to generate an anti-noise signal. The signal is transmitted from the relays to a custom earphone receiver ahead of the generated sound waves. They achieve their claims with mixed results due to limitations in hardware and experimental setup.
The overview of noise cancellations is the main idea or the core idea of active noise cancellation is to use an Internet of Things device in the environment that will collect data, and here required the sound data, and process these data over its wireless channel instead to wired channel. The active noise cancellation takes the advantage from the fact of the wireless signal travel faster than the sound signal. And because this aspect or this fact, the noise cancellation device take this advantage from it and become powerful to receive the sound signal with a few milliseconds in advance of its actual arrive time. And this feature makes noise cancellation devices leverage with the three amazing properties. These properties are timing, profiling, and channel estimation. The timing include in the ANC devices has robust digital signal processing. The process compute the ANC calculation very fast and work with a high frequency. Profiling, this aspect allow the ANC device anticipate the alteration or modification in the sound signals and handle these change with the DSP processor smoothly. Channel estimations, it's provide the ANC device with better and longer foresee. This feature can enhance the noise cancellation calculation due to the effect of the inverse channel estimation. The noise cancellation primer includes, in generally as shown in the figure 2 in slide 5, it includes 2 microphones and 1 speaker. The reference microphone receives the noise signal and then pass it to the DSP processor, and DSP goes to extract the sound signal from the microphone reference and determine the anti-noise and pass it to the microphone error. The anti-noise cancellation algorithm includes the reference microphone receive the noise signal through the channel as it's shown in the figure 3 in slide 6, and that's the NAC algorithm. It's embedded in the DSP processor to adjust the received noise signal with the adaptive filter. The error microphone receives 2 signals. The first one is from the noise source, as indicated as AT in a figure 3, and the second signal is from the anti-noise speaker BT. For the perfect cancellation, the sum of the input signals AT and BT, it has to be 0. The look-ahead algorithm. The mute system provides a basic modification to architecture of the old system. The modification includes separate the reference microphone from the headphone, and the reference microphone can be placed close to the noise source. Then use the wireless connection between the microphone reference and the DSP processor instead of the wired connection. These steps remarkable increase the look-ahead time and make advantage in the timing and cancellation. In the figure 4a, it shows the old or the conventional ANC system. The headphones reference received the noise data at time t1. The noise data transferred by wire to the DSP processor at time 2. The ADC analog to digital converter delay happened between T2 to T1, and the DSP processor calculate the anti-noise sample and transmit it to the anti-noise speaker at T3. The output will be AD AC digital to analog converter. The speaker must be able to play the anti-noise at time 4, but in the most cases, and that's what is the most of difficulties about the traditional ANC systems, reaching to this deadline is complicated because the distance between the reference microphone and speaker is less than 1 centimeter, and this inaccurate deadline has total effect on ANC performance, and it is the main struggle issue in the ANC system. In figure 4b in slide 7, explain the mute surely solve the time deadline of the conventional ANC systems by changing the reference microphone's position. Within this change, the reference microphone able to collect the noise signal earlier and forward it through the wireless link. In this case, the look-ahead has enough time to process the ADC, DSP, DAC, and speaker delay. Mute capable to calculate the anti-noise sample and play it at the same time of actual noise arrive at the speaker at time 6. The anti-noise synchronized with the noise as the black and red rows displayed in the figure 4b. Look ahead aware anti-noise cancellation algorithm. The noise cancellation algorithm includes the two important opportunities: the adaptive filtering with the future samples and the predictive sound profiling. The adaptive filtering with the future samples. Basic filter, the basic filter is just about averaging filter, and this is called causal because the output samples only depend on the past input samples. And also includes non-causality, and the non-causality is just basically require the future samples to recovering original signal. Adaptive filtering. This filter works based on the estimation the filter vector at a given time and convolve this estimated vector with the input signal, then do some comparison with the output signal against an interstinct or the goal signal. The LANC design is used to glimpse into the future and use the new sound samples to update the filter coefficient. Here in slide 11 it shows how the LNC algorithm work. Just basically take the signal from the speaker and record the error and do some comparison and do the calculation for the adaptive filter, and then find the coefficient. And the predictive sound profiling, this opportunity overcome the complicated noise source such that complicated noise source issues such as mixed source, as what happened with the people conversations with the presence of another noise. In the figure below, in these two plots in the slide 12, it shows how's the filter tabs versus the errors. Like in the first tab, it shows the filter not precise, so the error is very high. But it's when the filter response, it's really when it's become stable or close to the ideal case, the error got to converge as shown in the 0.3. Thank you.
Next, we'll talk about the architecture of the mute system. Basically, it involves three key components. That would be the wireless relay hardware that will listen to the ambient noise in a room, create the RF anti-noise signal and transmit it to the earphone. The automatic relay selection. So if there's a lot of sound sources in a room, as there are, and you have a lot of these wireless relays, they're going to need to know which one takes priority to transmit to the earphone, so the earphone's not receiving a bunch of RF signals at once. And also privacy protection, because they're proposing that this would be in a public space. They need to make sure that you can't intercept, these RF signals. Essentially, you're amplifying any conversation that's in a room. So that's something that is pretty vulnerable. A little bit more about the wireless relays. So they compose a reference microphone, an amplification stage to boost the incoming signals, so that'd be anything in the room, and then it'll go through a low-pass filter to filter out any high-frequency artifacts and let the actual usable content go through. Then there's an impedance matching circuit, which will connect the filtered audio signal to a VCO, and that VCO will help modulate the signal to an FM frequency and clock it with a PLL to 900 megahertz, which is an ISM scientific band. It'll then pass through a bandpass filter to get just a little bit more filtering, and it is boosted up and transmitted to the earphones. When it comes to the wireless relays, knowing which one takes priority to transmit the anti-noise signal to the earphones, they needed to come up with a couple DSP algorithms built into these wireless relays. So essentially they're going to use some fancy correlation, that would be the GCC FAT, that's PHATT cross correlation, and what it'll do is correlate the wireless transmitted signal against the signal captured at the error microphone. If there's a spike either positive or negative, that indicates that a sound source is coming from a particular direction. So if we say that a sound source is coming from one side of the room, if the first wireless relays get a positive correlation before the error microphone, we would say that those are the closest to, the sound source was closest to those relays, so they get priority. And negative correlation, so anything that would be closer to the earphone than to the wireless relays, those get ignored and they don't get transmitted. As mentioned, privacy protection was one of the key concerns of this research. The researchers claim that their wireless relays do not actually store any of the audio they're processing, so it's simply transmitted. In that case, we're not too worried about anything being recorded to be used later. However, because we're using RF, especially an open RF band, third-party interception is a critical concern, especially since we're going through the trouble of boosting human talking level signals in a room. Someone outside could just snoop in on what you're talking about and potentially record them. They say that, with some better technology such as power control, beamforming, sound scrambling, that wouldn't be a worry, but they also left it to future work. Next, we'll talk about how they set up their experiment, and we'll start with the hardware selection. So they made a good effort to use a lot of off-the-shelf components for the experiment, and as we get to the discussions part of this, that kind of hurt them in the end. But essentially, they claimed they use a Texas Instruments DSP board, some MEMS microphones, a speaker which they got off of Amazon Basics, or an Amazon Basics speaker which they got off Amazon to produce arbitrary sounds. They also picked up a Bose noise canceling headphone to shoot out between their earphone and the Bose consumer product, and they used a 3D head model to model the human head, and they put a reference microphone inside the ear of the human model. So for the actual experiment, the researchers played various ambient sounds to simulate noise you would have in a room, and this includes both speech and some forms of white noise, some black noise. And what they did was they measured the power level at the 3D head model using the reference microphone that was inside. And the reason they're doing the power level is because theoretically, if you created a quality noise canceling signal, you should have a lower power level received that's piped through the earphones, because it's actually actively canceling the signal it received from the transmitter. They also had 5 volunteers come in and kind of give these subjective quality opinions on the Bose system and their mute system. And the 4 key factors they set up 4 mini experiments, and that was using their mute system, running their custom LANC algorithm, the Bose with the active noise canceling enabled, Bose with active noise canceling disabled, so they were just interested in the actual materials, how noise isolating the materials of the Bose headphone were, and then they ended up running their LANC algorithm through the Bose headphones. So the most interesting result from their experiment was the wideband, that's 0 to 4 kilohertz noise results between the Bose and the mute system. So the graph you see here shows the frequency response between 0 and 4K of those 4 various systems. So there's the Bose with active enabled, Bose with it disabled. They have the mute hollow and mute passive, so that's the LANC algorithm running through the Bose would be the mute passive, and just the mute with the LANC algorithm running would be the hollow. So what they found was that the Bose headphones with the active noise canceling built inside were only effective for frequencies less than 1,000 kilohertz, while the mute passive one, that's where they were running their algorithm through the Bose headphone, was the most effective across all the bandwidths. So we have some criticisms of the experimental results, and in the paper you could see all the results in more depth, but specifically I'll highlight a few. And that's that the entire nature of the study was highly subjective. Noise canceling and sound in general are incredibly subjective. The quality of noise canceling, even though you're just canceling a signal, doesn't necessarily mean that it could be useful or pleasant to a consumer, for example. That's one way noise is just subjective in general. For their more subjective 5 volunteer studies, they just use a 5-star scale. That's just such a low N factor for a study like that, and I would like to see more volunteers down the road, certainly, to evaluate that. So we didn't think it was too significant to report on those results. They also admitted that a lot of the hardware they used was particularly cheap and diminished some of the possible noise cancellation between their devices, and that would include the Bose system. If they're not using quality hardware for sound, you're not going to get quality results. That'd be a garbage in, garbage out situation. Our third criticism is the very stationary setup they had. So they would vary the distances between the speaker and the 3D model head, but it was just very fixed. There were no dynamic movements of sounds from around a room like you would expect in a public space, which is what they're proposing this device is for. So to quote them, instead of physically moving the noise source or the wireless relay, we fix their positions. So that's another just kind of skewed data point. All the results were positive, which is a little skeptical. I'm a little skeptical of in general. But with these concessions, they kind of really gamed the results in their favor, I would say. Not to diminish how cool their technology is, but I think that it needs more in-depth study to be very cool. So they disclosed some limitations with their research. Top of the list would be that multiple noise sources would be a challenging problem for their DSP hardware or DSP software and the hardware they're using. So we're talking multiple microphones, multiple processors, trying to crunch some very expensive calculations. That would be your FFTs. Anytime you're going to invoke correlation, there's just a lot of overhead going on. Second would be the cancellation of the human ear and humans moving their heads around a lot in a more natural way. That really does start to change your transmission of the RF, how it's received, how humans hear things at different angles as they tilt their head. The human ear has some acoustic properties that they didn't account for that would definitely impact the subjectivity, the overall quality of the noise canceling. The portability of the system, so as they have it, they have a proprietary earphone that needs to be powered by something. They didn't disclose how it was powered, but it would have to be. And then they have these wireless relay stations, and they don't go into how many they would think they'd need to fill a room or whatnot, but we could assume that you would need at least 3 or 4 to get any reliable information from. And lastly, the interference in that 900 megahertz ISM band. So public spaces are noisy from an RF standpoint, and in these ISM bands, there's a lot of competing devices. So it's just something to consider. And they identified it, and I hope that they actually address these problems later on with this research. So to close, they were successful in the very limited scope of their experiment, we believe. There were some drawbacks. They kind of definitely limited the positive outcomes, or they limited the results to positive outcomes, despite all of the limitations of their hardware. And we think, if they spend a little bit more time and upgraded some hardware, fixed some of the software, it could be a pretty promising project or product in the end. And it's pretty exciting to see these sort of IoT solutions going forward. All right, that's it for us. Thank you very much.